So as I was just saying, we're going to learn about light as a visible part of the spectrum, but that actually this is just a small part of the electromagnetic spectrum, and in fact it's made up of a large number of other bands of frequency. So technically it's a continuous spectrum, so it's a continuous variable. It's a bit like height. It doesn't just come in discrete or set intervals, like eye color, for example. It's a continuous spectrum, but we group that continuous spectrum into certain bands, and we give those certain names. Okay, we're going to be looking at comparing the energies, wavelengths, and frequencies of all of these different bands. And we're also going to be looking a little bit at optical fibers. Optical fibers being really important for telecommunications, especially today. So you've probably heard of fiber optic broadband, okay, and you know it's very fast, but how does it actually work? Well, it uses optical fibers. We're going to be looking at how those work. We're also going to be looking at splitting up visible light into all of its colors. So you'll have seen this naturally as a rainbow in the sky. Okay, so we're going to be looking at all of those colors. And we're also going to be looking a little bit at the behavior of light at certain objects. So whether those objects are transparent, like glass, translucent, or opaque, where you can't see anything at all. Okay, so let's get started. So electromagnetic waves. So what makes them so interesting? Well, they differ from the other kind of waves that we're normally used to dealing with. Those are called mechanical waves. Okay, and mechanical waves travel through a substance. It's sometimes known as a medium. Okay, I'm not talking about the sort of spiritual medium, but a medium is just some form of carrying a wave. Okay, and multiple mediums, we don't say mediums, we say media, okay, which is also where we get the word media from. So as we can see here, some typical examples: waterways obviously need water in order to carry those waves. Seismic waves, so earthquakes, etc., need the earth to travel through. And sound waves require air, which is why in space nobody can hear you scream, because there's no air in space and therefore no sound waves. Now, we all thought in the sort of Victorian era that, well, every wave needs some kind of substance, some kind of medium to travel through. And electromagnetic waves, light waves, also we also thought that there had to be something to carry those waves. We called it the luminiferous ether. Okay, ether. And that was the hypothesis that for sound waves you need air, for light waves you need this weird thing called the luminiferous ether. But it turns out that actually it doesn't exist at all. Okay, there is no ether. And in fact, electromagnetic waves can travel through a vacuum, okay, travel through space, otherwise known as a vacuum. So they don't need a substance to travel through, okay? So electromagnetic waves can really just travel by themselves, okay? And that's what makes them so interesting and so special. Okay, and some examples of electromagnetic waves, well, it's just any of the waves from the spectrum that we're going to be looking at in a moment. So light waves, radio waves, X-rays, microwaves. I'm sure you've heard a lot of these before. Okay, so that's how electromagnetic waves differ from the other kind of waves that we're used to. Now, visible light is a certain range of frequencies in the electromagnetic spectrum, okay, and it makes an electromagnetic wave. So the electromagnetic wave sort of looks something like this, and it's a little hard to draw, but I'll give it a go. So we've got a wave going something like this, and another wave that is 90 degrees to the first wave that looks something like this. Okay, so we often do these lines to show how one is perpendicular to the other. Okay, so if I was to look at this head on, I'd have one wave going up and down like this and another wave going at a right angle to it. So one of those waves is the electric field and the other is the magnetic field, okay, E and B. Okay, so that's what an electromagnetic wave is. It's some electric field oscillating and a magnetic field oscillating perpendicular to it. And then they travel in a direction that's perpendicular to both, okay? So one of the main properties that we see is that electromagnetic waves are transverse waves. Okay, so remember the definition for a transverse wave. It is that the oscillation is perpendicular to the direction of travel. Okay, so if the wave is going in this direction, the oscillations are like this. Okay. Now, as we already said, electromagnetic waves don't need a substance to travel through, so they can travel through the vacuum of space. The reason for this is a little advanced, it's a little complicated. If you guys go on to study A-level physics, you'll learn a little bit more about this. But it turns out, to give you a basic idea, is that the electric field, as it oscillates, creates the magnetic field. And the magnetic field also creates the electric field. So one kind of creates the other. They are inextricably linked together in this unified force that we know as electromagnetism. And that's something that you would study at a higher level. But for now, all we really need to know is that there is an electric field and a magnetic field that oscillate as a transverse wave perpendicular to each other. Okay. Oops. There we go. So transverse waves, the direction of oscillation is at 90 degrees to the direction of energy transfer. So the direction of energy transfer, we can kind of just think of as the direction of the wave, or direction of travel, if you like. So this wave here is moving in that direction. So obviously the energy is moving towards the right. The wave is moving towards the right. Now this is different from the other kind of wave, which is known as longitudinal wave, where the direction of oscillation is at parallel to the direction of energy transfer. And the most common example of a longitudinal wave is a sound wave. Okay, so you've probably seen before that sound wave is the oscillation of air particles. Okay, and the air particles oscillate sort of side to side like this. And there'll be moments or positions where the air particles are densely packed together. Okay, this corresponds to an area of high pressure. And then there will also be areas where there is a low density of air molecules, and that's low pressure. So it's this shift in pressure caused by this longitudinal wave that we perceive as sound. Okay, so that air pressure goes into our ears and it vibrates our eardrum, which then we hear as sound. Okay, so that's a longitudinal wave, but we've got to remember transverse wave is what we're really focused on today. Okay, so electromagnetic waves are sometimes referred to as electromagnetic radiation, and in particular the higher frequency electromagnetic waves are often present in nuclear radiation. So you may have heard of things known as gamma rays. Okay, we're going to be looking at the whole spectrum in just a moment, but gamma rays are quite present in nuclear decay. Okay, so it's a way of atomic nuclei releasing energy. And the gamma rays, because they are so high frequency, they have a lot of energy. Okay, and that makes them quite dangerous to human beings. That's why we've got to contain them with thick walls of lead, etc. Okay, so sometimes we call it electromagnetic radiation, sometimes we call it waves. They are interchangeable. Okay, it's the same thing. Okay. Now, radiation is a specific kind of energy that does not need a medium to transmit energy through. Okay, so that's an electromagnetic wave. Okay, and how we transfer energy is known as radiation. Okay, so there are three main types of energy transfer you've probably come across. So you've got conduction, you've got convection, and you've got radiation. Okay, conduction and convection both require a medium to travel through. So conduction usually works best in solids. Okay, so you've looked at how heat is conducted through a metal rod, for example. Convection requires some kind of fluid. Okay, so air or water, and you've probably seen these convection currents before. But radiation doesn't require a medium at all. So it can transmit energy through the vacuum of space, but it's often the least efficient form of energy transfer. Okay, so usually conduction and convection are the most efficient. But radiation is exactly how we feel the heat from the sun, for example, because obviously there's a lot of space between the Earth and the sun. So that energy that we get from the sun is all from radiation there, not conduction or convection. All right, so finally, let's have a look at the whole electromagnetic spectrum. Okay, so as I said, it's a continuous spectrum because the wavelength, okay, remember the wavelength is just the distance between two like points on a wave. So these 2 points here, for example. So the wavelength continuously changes. We see we go from long wavelength to short wavelength continuously, but we split this continuous change into discrete categories that we see here. So we're going to look at all of them from radio waves all the way through to gamma rays. Okay, so let's just understand some of the vocabulary that we use when we talk about the waves. So the wavelength, as I've just said, is the distance between two light points on a wave. Okay, but then what about the frequency? Well, the frequency is about how many full wavelengths you get per unit time. Okay, so if you imagine a wave passing a point, how many wavelengths am I seeing passing that point per second? Okay, that's the frequency. Now, obviously, the shorter the wavelength, I'm going to get more wavelengths passing that point every second. So a shorter wavelength corresponds to a higher frequency and vice versa. Okay, so we can see in the arrow here how when we get longer wavelength, we get lower frequency, and shorter wavelength correspond to high frequency. And we also importantly see the energy change. So radio waves are the lowest energy electromagnetic waves, gamma rays being the highest, okay, and therefore the most problematic, okay, in terms of human health. All right, now let's talk a little bit about the speed of light, okay, because the speed of light is a very special constant in physics, okay, an important number in physics, as the slide says here, okay. It's important for a lot of reasons, but this is basically the universal speed limit, if you like, of the universe. So the fastest anything can move in the universe travels at the speed of light. Okay, and there's a pretty interesting theory that talks about how things change when you get to those speeds, known as special relativity. That was devised by some little-known guy called Albert Einstein. But unfortunately, it's quite complicated and we can't go into it in this course. But perhaps this will make you intrigued to go and study a little bit further. So the speed of light in a vacuum is approximately 300 million meters per second. It's quite fast, okay? It's enough to travel around the world 7 times in a second, okay? So this is really the fastest thing anything can move through space. And it also turns out that electromagnetic waves travel at this speed, and all the parts of the electromagnetic spectrum travel at this speed in vacuum. Okay, so it doesn't matter if you've got radio waves or gamma rays, okay, they both travel at the speed of light because the electromagnetic spectrum is light. Okay, so by definition, it must travel at this speed. Okay, so this is an important number to remember. In scientific notation, it's often written as 3 × 10⁸ meters per second. Okay, so you might see it written down like that as well. Okay. So let's have a look at the spectrum in a little bit more detail. So we start off with radio waves. Okay, so these have the longest wavelengths in the electromagnetic spectrum is really of the order of 1 to 3 meters. Okay, so this is actually quite large wavelengths, particularly compared to gamma rays, which we'll look at in just a moment. So the wavelength and the frequency, we've already seen how they're somewhat related, but let's have a look at how it's related quantitatively by a wave speed equation. So the wave speed v is equal to the frequency multiplied by the wavelength. So we can write wave speed as v here. But when it comes to electromagnetic waves, we know that the wave speed of all electromagnetic waves is the speed of light, okay? And in physics, because it's such a useful number, we actually give the speed of light its own symbol, okay? It is in fact just c, okay? So c represents the speed of light in vacuum. And so that's going to be equal to the frequency, which we call f, and the wavelength has its own symbol as well. It's actually a Greek letter. It's the Greek letter lambda, and it looks a bit like this. So you may see this equation written as c equals f lambda for an electromagnetic wave. Okay, so this is quite useful in some calculation questions where you're given perhaps the frequency of an EM wave and you need to find its wavelength or vice versa. Okay, right, and unfortunately I've written over this, but as wave speed is constant, a large wavelength means a small frequency. So we've seen how as one grows, the other shrinks. That's known as inversely proportional. Okay. So radio waves have the shortest frequencies, okay, because it's got the longest wavelength. Okay. Now the energy of a photon, okay, we'll come back to this in a minute, is given by the formula E equals Planck's constant multiplied by frequency. So this bit here, what's this photon? Okay, what's going on here? So for reasons that we won't go into today, it turns out that light can be thought of both as a wave and a particle, depending on what situation you're looking at. It's a quantum mechanical effect known as wave-particle duality. So we sometimes talk about light being made up of particles known as photons. So a photon is a particle of light, and the energy of a photon is given by the formula E equals hf, where h is Planck's constant. It's a very, very small number. H is something like 6.63 times 10 to the negative 34 joule seconds. Okay. So it's a very, very small number indeed, and the details of all of this is beyond this course because it requires a lot of quantum physics, okay? But the main point is that the smaller the frequency, the smaller the energy. So the energy, we say, is proportional to the frequency. So radio waves, okay, have the lowest energy, okay, because it has the smallest frequency. Okay, and this means that it provides little to no danger to life. We say that it is non-ionizing. So we're going to be talking a lot about what ionizing radiation is. Okay, so you're probably already aware of what an ion is. An ion is a charged atom, and we can charge an atom usually by adding or removing electrons from that atom. Okay. Now, if I fire enough electromagnetic energy at an atom, okay, I can actually remove some of its electrons, and that ionizes the atom. Now, why is this such a problem to human beings? Well, if you ionize an atom, you change the chemistry, you change the bonding of the atoms, and if you're changing the chemistry, you're going to be changing the biology. So this can actually lead to corruption of DNA and can lead to things like cancers, for example. So we've got to be very careful when we're dealing with ionizing radiation. But radio waves, being so low in energy, don't really present such a problem to us. Okay. So what do we use radio waves for? Well, obviously radio, hence its name. Okay. And we can actually use this in other broadcasting as well, but generally we can just say communications is the main use of radio waves. So we've got radio, of course, but also TV is sent via radio waves, satellite transmissions, remote control toys, MRI scans, and mobile phone signals. And one of the interesting properties of radio waves that makes it so good for long distance communication, so it's great for long distance, is that radio waves can actually reflect off the part of the Earth's atmosphere known as the ionosphere. Okay, so it reflects off, which means I can send a signal. Okay, so maybe here's my dish. Okay, here's my receiver. I can send it over much greater distances because if I can reflect it off the Earth's atmosphere like this, I can actually get around the curvature of the Earth that would become more of a problem at longer distances. I wouldn't be able to send it directly because it would just hit the Earth's surface. So that's why radio waves are so good for long distance communication. All right, let's move on to microwaves. So as we're moving from left to right here in the electromagnetic spectrum, we are decreasing the wavelength and increasing the frequency. Okay, so microwaves have shorter wavelengths than radio waves, but are longer than infrared waves. Okay, so larger frequency, lower wavelength. And therefore, because we're increasing the frequency, we are also increasing the energy. Okay, so as we move from left to right here, we're getting more energetic. So what are microwaves used for? Okay, well, I think the first use case that comes to mind is, of course, the microwave or the microwave oven, to give it its full name. Okay, so how do these work? So microwaves penetrate the food and their energy is absorbed by water molecules. So you've got your microwave oven here. Okay, and what it does is it sends microwaves, and your food here will absorb the energy from those microwaves, but it's the water molecules in those microwaves. It's the water molecules in the food that get heated up. Okay, it's often why things can get a little bit soggy if you're reheating things in the microwave. It's because it's mostly activating those water molecules. Okay, but there are other use cases for microwaves as well, such as satellite TV, radar as well. Okay, so again, you want something with a fairly long wavelength, okay, that can go for a long distance. So microwaves are a good part of the spectrum to use for such things. And we've also got mobile phone signals, Bluetooth and Wi-Fi. So generally these lower, so these four here, these lower lower frequency wavelengths, okay, are best used for communications. All right, let's keep going. So infrared. So infrared you've probably heard of as something related to heat. Okay, you've probably heard of infrared cameras, for example, which sort of render the world in these kind of weird colors depending on how hot something is. Okay, so all objects emit infrared waves as infrared radiation, and the hotter an object is, the more infrared it emits. Okay, the sun, for example, mainly emits infrared, visible light, and ultraviolet radiation. So all of this is to say it's something known in physics as black body radiation. So basically everything with a temperature above absolute zero emits electromagnetic radiation as part of its heat. So this isn't light that's reflected off a person. So you're seeing me now with visible light because there is visible light bouncing off me as a person and reflecting into the camera, and then you can see me. Okay, but I am also emitting infrared radiation, which you cannot see. Okay, and this is because of my heat. Now, we can sometimes see something because of its heat when it gets very, very hot indeed. So you've probably heard of the expressions of something being red hot or white hot. Okay, So this is because the hotter something is, the higher frequency radiation is emitted due to its heat. But most objects such as humans and animals, etc., even planets, for example, because of their temperatures, they mostly emit in the infrared spectrum, which is why we can't see it. Okay, we have to use a special device such as an infrared camera that can detect that infrared radiation. Okay, so what can we use infrared for? Okay, sorry, no, I'm ahead by a slide. So let's talk a little bit more about the temperature here. So infrared is next to red in visible light. So we'll be looking at visible light and all of its different colors. And this is also why it's called infrared, because it literally means further on than red, which is also why as we heat something up, it first becomes red, okay, and then moves to white. Okay, so something being red hot is actually cooler than it being white hot. So as something heats, it comes from infrared, then it goes into visible red, into white, then into blue, okay, and then into ultraviolet. So ultraviolet you could think of as being bluer than blue. It's sort of on the other side of the spectrum. Okay. Now, although humans can't see infrared, some animals can, such as rattlesnakes, goldfish and piranhas, which gives them some advantages. So they can actually spot animals, even if you can't see them with visible light, okay, because they're hiding behind something, okay, that you will still be able to see the infrared because it will be able to penetrate through certain objects. You may have seen an example that if I put my hand into a bin bag, obviously my hand disappears behind the bin bag, but if we were to view it through an infrared camera, the infrared radiation actually passes through the bin bag. So somebody with infrared sight, for example, would actually be able to see my hand behind the bin bag. Okay, so obviously it gives certain animals a bit of an advantage there. Infrared radiation can promote immunity and healing in the body, okay, which is a little bit why, you know, going outside is good for you. But it can damage your eyes, okay, so this is why we sometimes have to wear eye protection, such as sunglasses, when going out and about. All right. So let's have a look at now at some of the uses. So electric heaters, so a lot of things to do with heat. Okay, so electric heaters such as, you know, the outside heaters that you might get often use infrared radiation. They are very often used in remote controls for TV. Okay, so that's a good one to remember. And optical fibers. So we'll be coming back to optical fibers a little later on, but infrared is a very commonly used frequency for optical fibers, which carry your Wi-Fi signal, for example. Okay. Finally, let's move on to visible light. So as we can see, there's actually the majority of the electromagnetic spectrum we cannot see, but there is this small bit in the middle that the human eye can. Okay, and we know that visible light is in fact split into its own spectrum, this kind of rainbow, going from red all the way to violet. Okay, so obviously if we go further to the red side, okay, we go into infrared, and if we go further to the right from violet, we go into ultraviolet, hence the names for these sort of things. Okay, you should know that the wavelength of visible light varies from 700 nanometers to 400 nanometers. So you should have that vague range in your head, because sometimes you'll be asked whether something will actually be visible or not. Okay, so if you have a frequency of some electromagnetic wave, you can use C equals F lambda to calculate its wavelength, and then you'll have to know, does this wavelength fall between 700 and 400 nanometers? Okay, remember that 1 nanometer is 10 to the minus 9 meters. Okay, so quite small indeed. And we have the typical spectrum here: red, orange, yellow, green, blue, indigo, violet. which is often remembered as Richard of York gave battle in vain. Okay, so these are of course the colors of the rainbow. Okay, and the rainbow really just shows the full spectrum of colors in the visible spectrum there. Okay. So light that comes from the sun and lamps is known as white light. Okay, and white light contains all the colors. Contains all colors. Okay, so the whole spectrum together creates white light. Okay, and these different colors come with different frequencies. Okay, and we group them into the 7 different colors. Again, we have a continuous spectrum. So exactly when red becomes orange and orange becomes yellow and yellow becomes green, etc., it's sort of hard to say. We do have cutoffs, okay, but those are imposed by us. We've sort of come to a consensus on when those things become one color or the other. But actually, to the human eye, I could show you 2 different shades either side of that cutoff point, and they would look more or less the same. Okay, the human eye can only detect so many unique colors. Okay, so red has the largest wavelength and the smallest frequency. Okay, and violet has the smallest wavelength and the biggest frequency. So as we go from left to right here, the frequency is increasing, the wavelength is decreasing. Okay, and therefore the energy, okay, must be increasing as we move towards the right. Okay, and there is the little mnemonic that we use to remember the colors. So Richard of York gave battle in vain. But you can come up with your own. I encourage you to use all of these. Okay, use the first letter of each to come up with your own mnemonic. Could be anything. I'm not going to try and do one now. But anything that works for you really is the best. Richard of York gave battle in vain is just a very common one, but whatever works for you. Okay, so a question for you. So which color of light has the largest wavelength? Green, indigo, or yellow? Okay. Okay, I've only got about 30 of you, but I know there's quite a few more of you than that. So do please try and respond to these questions, okay? Keeps you engaged, keeps you learning, and it also helps me to see if you guys are understanding this. This is sort of our main way of being able to communicate. All right, so I'll just give this a few more moments, and then we will have a look at the answer. So with the diagram, this should be pretty easy. But of course, you will need to be aware in your exam which would have the largest wavelength without the diagram. In other words, you've really got to commit this to memory. Okay, that's about 60 of you, so let's have a look. Okay, yellow, of course. So it's, as the vast majority of you have got there, okay, we just need to look at which has the largest wavelength. Well, the largest wavelength is towards this left-hand side of the spectrum. It's towards the red end of the spectrum. Okay, so red has the longest, and then it gets progressively shorter as we move to the right. So we see green, indigo, or yellow, while as we move from left to right, well, the first color we come across is yellow. Green comes afterwards, and indigo after that. Okay, so yellow must have the largest, then it's green, and then it's indigo. Okay. Now, if the question instead asks for the largest frequency, then it's the other way round. Okay, we have to move from right to left. So the right-hand side has the largest frequency, and then it gets progressively smaller as we move to the left. So there we would see indigo would have the largest frequency there. Okay. So yellow is the correct answer there. Okay. So we talked about how white light is contains all of the colors, okay, and we've proven this, and we've actually known this for hundreds of years, partly thanks to the experiments performed by Isaac Newton, no less, okay, using a glass prism, okay. So when we shine white light into a glass prism, it actually splits into all of these colors here. So here we've got Richard of York gave battle in vain. We've got all of the colors of the rainbow once again. Okay, so we can use a glass prism to show that white light's made out of all of these colors, but also rainbows itself, okay, have a similar effect. So raindrops also make this kind of pattern here. So this is known as dispersion. Okay, so when we split white light into its individual colors, okay, we call that dispersion, and it's due to something known as refraction, and we'll come back to refraction towards the end of this presentation. Okay, perhaps some of you have heard of it before, but this is why white light will disperse into all of its colors, and how we know that white light is in fact made out of all of these different colors. So what can we use visible light for? Well, what can't we use it for? So obviously visible light is the one we can see, so it's very useful in that sense. And we can use it for all kinds of things. So lasers, for example, photosynthesis, so plants actually live off visible light. Optical fibers as well, so we use infrared and visible light. Which one we use kind of depends on the specific situation. Computer screens as well, obviously we need to be able to see those. I think you can come up with several examples of your own where we would use visible light. Okay, so we talked a little bit about optical fibers already in this presentation, but what exactly are they? So really, at its basic level, an optical fiber is simply a thin rod of glass, but very, very high quality glass, very pure. Okay, so we would normally think that our windows are pretty pure, we can see through them just fine, especially when you clean them. Okay, but optical fibers are very high grade pure glass. Okay, and we need them to be so pure because any imperfections in the glass would disrupt the signal that we send down an optical fiber, and that can have major repercussions. Okay, so that's why they're pretty special and a little expensive. So how do they work? Well, they work by transmitting signals in the form of light rays. Okay, so we can just send electromagnetic radiation down these glass rods, okay, and that's how we carry our signal. When we talk about digital information, okay, how does that work? Well, remember that, you know, at its basic level, digital information is sent in bits, which are these ones and zeros, okay, etc., etc. So we send our, you know, signal down in sort of these ones and zeros. It's something we know we call binary. So anything that either has an on state or an off state can be used as a way of transmitting binary information. Okay, well, light's a good example because light can either be on or it can be off. So what we usually do is we send little pulses of light. So when the light is on, we have like a 1 state, and when it's off, it's a 0 state. Okay, so this is how we send digital information down an optical fiber in form of light. We send little pulses down, okay, and then there will be a receiver on the other end that takes in those pulses, transforms that into digital information, and then, well, the rest I think you're aware of. Okay, so let's have a look at the physics in a bit more detail. So light enters one end of the fiber here, so we've got it entering here. Then what's going to happen is it's going to strike the boundary of the optical fiber. Now, at the boundary, we have something known as total internal reflection, which means that all of the light is reflected at the boundary. So none of it refracts out of the tube here. Okay, all of it is reflected back in. Okay, so got the reflection here. It's now going to end up hitting this boundary here, okay, where it will also totally internally reflect. And here we see that the signal effectively bounces between the sides of the tubes and travels all the way down and eventually exits here where we will receive our signal. Okay, so total internal reflection here is the driving principle behind the optical fiber. Okay, so here's a definition here. It's a complete reflection of a light ray at a boundary with a less dense material. So often this sort of dark blue here, this dark blue bit here surrounds this light blue bit here. We sometimes call the light blue bit the core that carries the signal, Okay. And then the outer bit here is sometimes known as the cladding. Okay, and the cladding protects the core, but it also is less optically dense than the core, and that is important because that's what allows total internal reflection to happen. So you've got the core, and then the core is surrounded by a material known as cladding. Okay. Let's go back now to our electromagnetic spectrum. So we've looked at visible light, again, moving towards the right to higher frequencies and lower wavelengths. Okay, we have ultraviolet light. Okay, now ultraviolet light, we're now really getting into the energetic waves of the spectrum, and this is where we can have certain health issues crop up. Okay, so UV waves have enough energy to damage humans, primarily in the form of sunburn. Okay, so when you're out in the sun for too long, your skin becomes red due to being damaged by ultraviolet radiation. So when you put sun cream on, what the sun cream is doing is effectively absorbing a lot of the energy from ultraviolet light so that your skin doesn't take the brunt of the damage. Okay, that's why it's important to use sun cream. Okay. So UV radiation is emitted by the sun. Again, because the sun is so hot, it emits radiation in the UV spectrum. Okay, and this can be absorbed by the skin. Now, a little bit of UV is good, okay, because it generates vitamin D. It also stops you looking really pale and ill. Okay, so it's good for you. It's good to get out. It's good to have a bit of sun, but too much will get you sunburn and can lead to, in very extreme cases, skin cancers. Okay, so we've got to make sure that we protect ourselves. And finally, X-rays and gamma rays. Okay, now X-rays and gamma rays are so energetic that they actually travel through most substances. So in order to protect ourselves from X-ray and gamma ray radiation, we need a thick plate of lead. Okay, so we need a really thick wall of lead in order to absorb that radiation. Okay, now because they go straight through most substances, they're very useful for analyzing bones. Okay, because X-rays will go straight through your muscle, your skin, all of that tissue. Okay, but it will be absorbed by your bones. Okay, so it doesn't necessarily travel through everything, okay, but that makes it very useful for analyzing bones, because effectively you can put, say, my arm there, have X-ray radiation come down. Most of it will pass through except where my bone is, because that's where it's going to absorb the X-ray. Okay, and so I can sort of have a negative of that on my sort of screen, if you like, and there I can sort of analyze what's going on with the bone. I can see if it's broken. I can check out what's going on. Okay, But because they have such high energies, okay, we've got to be careful in our use of X-rays, which is why most patients are limited to a certain number of X-rays per year. So they'll make it, if you ever do get an X-ray, they'll make a note of that, okay, making sure that you don't overdo it, you don't get too much of a dose there. Gamma rays, okay, have the smallest wavelength of the electromagnetic spectrum and the highest frequency. They're particularly present in sort of nuclear reactions, okay, so nuclear power plants. We've got to protect against that. But they can also be used in medicine as well. There's something known as a PET scan that uses gamma radiation in order to analyze certain workings of the body, okay, to see how the digestive system is working or to see where energy is being used up in the body. It can actually be used to identify certain tumors, okay. So gamma rays, when they're under control and used in a precise way, can actually be very useful to humans. But again, there are dangers, so we have to be aware of those. Okay, so what are some of the differences? So X-rays are produced when particles are stopped when moving at high speeds. That's actually given a specific name. It's called Bremsstrahlung radiation. So when you sort of stop certain charged particles, such as electrons, you have this Bremsstrahlung radiation, sometimes just known as braking radiation. And often the radiation produced is in the X-ray spectrum. Gamma rays, as I've mentioned, are produced by radioactive substances. And gamma rays have a shorter wavelength than X-rays and higher energy, so can penetrate more substances. So when I was talking about the bone example, gamma rays wouldn't really be useful in that situation because they would pass through the bone as well. So I wouldn't really get any information out of using gamma ray in that situation. So again, it really depends on the kind of thing that you're trying to look at. Okay. Here we see how the X-ray works here, as I've sort of described already. Okay, so gamma rays, they do have uses. They're particularly good at sterilizing medical equipment because they have such high energy. They will kill bacteria or any germs that are on anything. Okay, so it completely sterilizes them. So this is obviously very useful for surgery. Okay, because if we're going to be, cutting someone open, okay, we've got to make sure that we've got a very clean scalpel. And as I said, using gamma rays to treat cancer, so you can use gamma rays to identify tumors, but you can also use them in the treatment of cancers. So radiation therapy often uses gamma rays to target the tumor. So there's a lot of physics. And in fact, there are even physicists that work in hospitals to make sure that the radiation is going in exactly the right place to target the tumor, but nothing surrounding it. Okay, so that's the sort of working principle behind radiation therapy. Okay, this I think we've already sort of talked about. So the dangers, of course, is because it's such high energy, it's known as ionizing radiation, and we've already explained how ionizing radiation can change the chemistry and therefore the biology of humans, okay, and therefore presents a great risk. Okay, so that's why people who are exposed daily to radiation, so for example, people working in radiation therapy or near X-ray equipment or in a nuclear power plant, for example, have to wear special badges known as dosimeters, okay, which measure the dose that's been absorbed. So you might see that if you're in well, I doubt many of you have been to a nuclear power plant, but if you were, you would see people wearing these badges that actually say the dose there. So they say it so everyone can actually see how much people have had as a dose. And then if it gets too high, they are required to leave the power plant and stay away for a certain period of time. Okay, so that's the electromagnetic spectrum. Okay, so we've looked at all of them from radio waves through to gamma rays. So just remember the overarching pattern. These waves all travel at the same speed. That speed being the speed of light, which we sometimes represent with the letter c.